So let's talk about drivers and radiative forcing. This is the net change in the energy balance of the Earth's system. It's the difference between the radiant energy arriving from the sun to planet Earth and then what flows from Earth back out to space. Our Earth is always trying to balance this thing in balanced climate, so it's trying to stay at a nice equilibrium. If you compare it to our mean body temperature, maybe 98.6, so it's trying to find a balance of whatever its temperature is that it can handle. We refer to the amount of radiative forcing in watts per square meter. So the watts per square meter is this big W/M with a superscript 2, and the greater the imbalance, the higher the watts per square meter. So a couple of things that we look at is a diagram like this one. You can see everything above the zero chart would be a positive forcing. That means that it's adding watts per square meter. Anything that's below the zero marker down here would be taking away from the heat factor, and they would be a negative forcing. It means it has a cooling effect. So it's not adding any more heat to the atmosphere. So again, positive forcings have a warming effect on the planet, and then negative forcings have a cooling effect on the planet. Those are guaranteed test questions. Our goal in science is to determine what's happening over a series of centuries, decades, to help plan for future needs of our populations. We know that scientists determined that forcings from the year 1750, because that marks the time in history when there was a rapid increase of fossil fuel use. That's called the Industrial Revolution. So what we've discovered is over that 300 and so 100 plus years, since we're currently around 2015-ish time, there are three major drivers that we've seen that are substantial to the picture of climate: greenhouse effect, ozone, and then aerosols, specifically particulate matter that has a dark color. So the number one forcing are the long-lived greenhouse gases. They're referred to as LLGG for long-lived greenhouse gases. There are three of them that are extremely important, and then we'll add in a fourth a little bit later. CO2, remember we don't regulate that with the Clean Air Act. Sources can come from even vehicles, fossil fuels, deforestation, even naturally occurring sources that are non-anthropogenic can be from volcanoes, natural forest fires, and so forth. Methane, sources of this come from fuel extraction and transportation, such as mining operation, flares that flare off methane like a landfill flare, rice cultivation, livestock, wetlands, landfills themselves actually give off methane. Halocarbons and NOx gases are another source, and those primarily come from agricultural and industrial processes. Together, all three of these things have had a positive forcing, so that means a warming to the climate of 2.6 watts per square meter on Earth, with the greatest of CO2 being the most important of them. So when you look at the greenhouse effect, the sun produces radiation for the Earth in a spectrum of wavelengths. So CO2 absorbs infrared radiation or heat of a particular wavelength. Some of our greenhouse, or some of the gases in our atmosphere aren't greenhouse gases. They let radiation pass right through. If there's more CO2 which does absorb infrared radiation, the more radiation the wavelength gets trapped in the atmosphere and the warmer it gets. One of those things that we're concerned about is water vapor, because water vapor naturally has some of that molecules that can allow for absorption in a very strong way of heat. So levels in the atmosphere are linked to temperature, and the temperature of warm air can hold more water vapor than cold air. So areas that have lots of water vapor that are warmer anyway can end up having a more significant impact from greenhouse effect, simply because there's more water vapor that can be heated up. Remember already that the Earth's surface absorbs 50% of solar radiation, but we need to think about what happens in between the ground surface and the top of the atmosphere. Clouds play a role in the climate picture as well. These are little droplets of water or ice particles that are stuck onto some kind of particulate matter known as the condensation nuclei. And what happens is they absorb heat from the Earth's surface and reflect heat back to space, preventing the warming of the surface. So if you have a bunch of clouds, that can actually be a positive thing. However, there's a lot of water vapor in clouds. The gases that make up most of our clouds, nevertheless, maybe not our greenhouse gases per se, but the water vapor themselves becomes an important greenhouse gas. So remember, warm air holds more water vapor than cold air. One of the things that we have to talk about in global warming or climate change is ozone, because that's the number one thing you hear about when you hear the word global warming. Ozone really, folks, is a short-lived greenhouse gas. It's not nearly as long-lived as something like carbon dioxide or methane or NOx gases. We mainly see bad ozone in the lower troposphere where humans are, because it absorbs a lot of heat. Because remember, ozone's O3, 3 oxygens stuck together. And we're depleting it in the stratosphere where we want it to knock out or to absorb ultraviolet radiation. Nevertheless, too much ozone down here in the troposphere has caused a counterbalance. And that has led to a much larger impact on climate. So you've got an increase in the net of the amount of watts per square meter that can occur. Understanding that tropospheric ozone, most of that comes from emissions of from the vehicles or from industry, manufacturing plants, so forth. And ozone is a primary component of smog. Smog is definitely part volatile organic compounds, some NOx gases, and then ozone. Aerosols are another important component that we need to discuss. The overall impact of greenhouse gases has been significantly offset by negative forcing of aerosols. So you might go, oh, yay, a good thing for a change. There are two types of aerosols. There are those that scatter sunlight, and then there's that absorb it. So you have to kind of look at it. It goes back to that color thing. Matter of fact, we call color, let's say the color of the Earth, it's albedo. And albedo, the lighter the color of the Earth, the more energy it's going to absorb. The more energy it's going to reflect, The darker the color of the Earth, the more it's going to absorb. Well, the same is true with aerosols. So if I have a light-colored aerosol, like volcanic ash, for example, it may coat the atmosphere for a brief period of time with a lighter color. And then when I have black sooty stuff, like you see right here coming out of the stack, which I might add, if you see visible emissions like this out of a stack, they've got a problem. In today's world, we have things that can fix that. Black sooty carbon-containing particles are going to absorb sunlight just like your dark shirts would during the summer months. So that would cause a positive forcing. If you have light-colored aerosols, they would cause a negative forcing. So how do forcings vary with time? It's an interesting question to contend. When you have volcanic forcings, that can just be a few years. So people always say, oh, we have a big mega colossal eruption in Yellowstone. It's going to cause climate change forever. It'll change it in the short term, but it won't last very long. That only takes a few years to dissipate that material. Aerosols, however, can take decades to actually fall out because of the microscopic nature of what those aerosols are made out of. Forcings are different for the ocean than they are on land because the ocean has an incredible capacity to hold heat. It's like our temperature regulating machine for planet Earth. So the mixing of surface waters with the deep ocean water is a very, very slow process. If interrupted, that can certainly change climate. If you saw the movie The Day After Tomorrow, that was very much the premise of the entire movie was a sudden shift in desalinization of the Atlantic Ocean. Oceans can take decades and centuries to fully respond to forcings. So let's say when we finally do hit a tipping point where the Earth's temperature just goes rampant because it can't control itself, so it gets a really bad fever, right? It may take decades and centuries for the ocean to recompensate for that. How will that affect humans? That's the whole premise behind climate planning, like the Intergovernmental Panel on Climate Change that we looked at just a few minutes ago. So that means that some of the climate change that happened during the 20th century on into the 21st century was actually caused by factors that occurred in earlier decades, causing forcings that are just now starting to surface. Imagine what that might mean in 10, 20, 30, 40, 50, or even 100 years from now. Now we need to talk about climate feedbacks and processes. A climate feedback is a response to a change that influences the change itself. So this is unlike a forcing, which had nothing to do with being impacted. This is actually impacting. A positive feedback occurs when a response accentuates or increases the original change. A negative one is when the response opposes or decreases the original change. One of the main factors that can cause feedback situations to occur is water vapor, because warmer air holds more water vapor. So additional warming occurs to the earth when there's more water vapor present. This would cause a positive feedback. So if I had an atmosphere that had very little water vapor, I would have a negative feedback. So let's say we end up having a period of millions of years where we're in a desert environment like we were back in the early Jurassic period. We would have had a negative feedback at that time. Even though we had hotter temperatures, we had very little water vapor in the atmosphere. So the hydrologic cycle is directly impacted by forcings and feedbacks, and the amount of water vapor that we have present in the atmosphere really leads to potentially more condensation and more frequent and severe weather patterns that we can have across the globe. While that may sound good, oh good, more rain, it can lead to a whole nother set of planning issues for humans, such as natural disaster planning and how to deal with other types of geologic phenomena of mass wasting like landslides, mudslides, tsunamis. The list just goes on. The strength of a feedback is important to the overall impact of the feedback, especially when we're talking about one that's going to cause an increase in temperature, which would be a positive feedback. So we're not talking about positive feedback like, oh, you're great today. We're talking about positive in terms of heat. If the positive or the heating feedback is just 10% of the initial change, that would mean a 1.1 degree centigrade increase. All right, so where I'm going with this is if you only have a 10% feedback, that's really not that significant. You're like, well, where is she coming up with that number? This is just an arbitrary number. That feedback is not a 10% of that change, but rather 0.11 or 0.10. So the response becomes 1.11, 1.111 every time you go up 1.1 degree. So it really is never going to get out of the 1 degree markers, what I'm getting at. If you have 100% positive feedback, it's different. And that's where we kind of are right now with our climate. This would cause a 1 degree centigrade warming and increases mean global temperature by 1 full degree centigrade. So that means if you have a feedback that adds 100% change, we've got a problem. And we're in that situation right now. So once I change from 1 to 2 degrees, I could reach 3 degrees when I reach another 100% feedback. So where I'm going with this, if I start with this number, and this is 100% more, I'm going to double it. So every time I double my amount of carbon in the atmosphere, the bottom line is I increase my mean global temperature by 1 degree centigrade. So we have to have a baseline number in which to operate from to determine what's going on with our climate in terms of potential heating up. The end result is that with this strong feedback, the temperature could continue to warm until something else changes. So what would change? The Earth would have a snapback process. Essentially, it's immediately going to warm the oceans. We're going to have a release of all that carbon from the limestone that stored it. So we'll have a super heated climate for a while. The Earth's got a super big fever. It's going to snap itself back into shape somehow to receive back that balance that it's trying to get. When it does, we'd probably end up in an ice age. That's typically what's happened across the board throughout geologic past. A couple more things to talk about. The Earth's cryosphere is a very big component of the climate story that we have, and places on Earth that are so cold that water stays frozen year-round are referred to as the cryogenic portion of our planet. Snow and ice can make up the cryosphere, but literally these areas exist below 0 degrees for at least part of the year. Classic places would be Greenland, and certainly Antarctica. Part of the Arctic Circle would as well. But Greenland and the Antarctic continent would be the two main places where year-round cryospheric ice can be documented. Why is that so valuable to us? If it contains long-term ice coring information, when we go get those ice cores, we can actually analyze climate shifts over a period of time. So that brings me to a place and a time in which we can't go back with ice cores, but we can go back with deep sea sediments and even surface sediments and fossils. So here is a case study in what happens with a runaway climate, and then we're going to apply that to where we are today. One of the world's most extreme global warming events ever was the PETM, known as the Paleocene-Eocene Thermal Maximum. I bet you're thinking, I never thought I'd hear of such a thing. PETM. This happened 55.8 million years ago. Test question, and why is the PETM so important? Well, we had a shoot up of temperature literally over 10,000 year period of time. Well, that sounds like a monstrosity of time and geologic time. That's not even a blink of an eye. To have temperature rise that fast, that'd like in human terms be you get a fever of 105 overnight. That's pretty much like what it would be like. So something went significantly haywire. In doing so, we lost a whole bunch of these animals right here. These are called foraminifera. And foraminifera are important to us for a number of reasons. One of the things is that we can document climate change with them. Another reason is they contain a little bit of nice amount of fossil fuel in them when they live. And so when they die, they sink to the bottom of the ocean floor and make hydrocarbons. So we can document a massive loss of them right in this section, which dates to right around 5.8 million years ago. So let's discuss what happened in the Paleocene-Eocene thermal maximum. We know that there was a large decline in global carbon isotope ratios in the ocean and land sediments, which indicates that this occurred due to a dramatic shift in the carbon cycle. If you're not familiar with the carbon cycle, it's important to planet Earth for living organisms as well as the manufacture of rock and climate control. Now, marine sediment cores from this time period indicate that it took at least 100,000 years for the excess carbon that was in the PETM's climate or atmosphere at that time to stabilize before the climate could actually get back to normal doing its business. All right, let's apply that to modern time. If it takes 100,000 years to get everything back to business as usual, will humans even be around? Modern Homo sapiens haven't been around but just 100,000 to 200 or so thousand years. So that's a pretty significant thing to think about. That begins to be the gloom and doom part of the climate story. There's still more to the story. During the PETM, ice core data supports that the carbon cycle amplified climate change more so than any other factor that was there. Humans run around with the Industrial Revolution to be producing anthropogenic pollution at the time, so the carbon came from somewhere else. We'll get to where it came from in a minute, but let's talk about how significant that carbon level was. 1,000 parts per million by volume. Think about that. You're like, well, I don't have anything to base that next to. Currently, currently carbon levels sit at about 390 parts per million by volume, and right at the beginning of the Industrial Revolution, they sat between about 290 to 320. So let's just make a nice 320 on the safe side. So every time we double that 320 number, we'll even make it 300, easy for math. So we go to 300 to 600. That would be doubling, right? So then you should have a 1 degree increase of mean global temperature. I double it again to 900 parts per million by volume. I should have another 2 degrees. I double it again, I'm going to have a 3 degree rise in temperature. That's going to put us over 1,000 parts per million. That was one of the worst global warming events of all time. I think you can see what I'm saying on order of magnitude. we are not too far from having another PETM occur on Earth if something's not done to try to reduce unnatural anthropogenic pollution. Because if we end up having a PETM situation in modern time, that means that all the naturally occurring methane and CO2 are going to join the club with the anthropogenic concentrations. We can't even begin to understand how that's going to cause impacts to Earth. Now, that's what climate modeling is all about. So if you want a long-term job security, that would be a great way to get it, is to get into the modeling business for climate shifting. So anthropogenic concentrations of CO2 levels are evident, especially in the Arctic Circle area, most importantly in Greenland. Geologic sediment and ice core data have indicated that CO2 levels must double to achieve a 1 degree increase. I guarantee you that's a test question. So it's that example of going from 300 to 600, 600 to 900, 900 to 1200. So all it's really going to take us is a 3 to 5 degree increase in mean global temperature to produce a massive heating up of our Earth's atmosphere. When that happens, remember the limestone that's at the bottom of the ocean is going to release an enormous amount of carbon. It's like 30 million gigatons of this stuff. It's incredible. It's a humongous volume of it. So now we're going to have all this naturally occurring stuff plus whatever methane clathrates are in the ocean in the form of ice. So let's get to them as well. The PETM was thought to have come from these pockets of methane gas that occurred from a die-off of animals that occurred at the end of the Cretaceous period, more than likely. And it is thought that the Eocene hothouse climate was caused by methane clathrates that were deep in the ocean, because this heating event that occurred happened at the very early portion of the Eocene epoch. So in geologic time, it goes, the last era of time is Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and Holocene, of which we are today. So the Paleocene borders right beneath it at the end of the dinosaur time frame. So we're looking at the very end of the Paleocene, the beginning of the Eocene, and that was right at 55.8 million years ago. So fossil evidence suggests a really interesting story about the PETM. The animals got tiny, the mammals, and the plants got huge. Isn't that weird? So why did the plants get so big? Lots of heat, lots of water vapor, lots of rain. However, the nutrient value is thought to have been fairly low, which made it caused the animals to shrink in size, or at least that's the hypothesis that's out there at this time. So I'm going to have you watch a video, stop what you're doing here, then this will actually be part of your testing routine, and you go to Unearthing Climate Change by the American Museum of Natural History. This is the actual link right here. If you can't get it to work, just type in a Google search, Unearthing Climate Change by AMNH, standing for American Museum of Natural History. It's about an 8-minute long video about the PETM and the research that they're doing on fossil evidence and soil sediments, indicating trying to learn about this past global warming event. So what does all this mean for you? If our current carbon situation is at 390 parts per million by volume, and it takes a doubling of pre-industrial revolution numbers, so we're going to put that around the 300-ish mark to make it easy to do the math, it only takes 3 jumps for us to get above PETM levels of 1,000 parts per million, and we know for sure that 1,000 caused a global warming. So that's scary. So you need to actually think about what that means to you, your family, what that could mean for growing crops. We're not going to be able to feed 7 billion people if this happens, especially with the shift in fauna and flora that will happen as a consequence of the nutritional value of these foods. So if your brain's going crazy over this, like, oh my gosh, what kind of technology do we need to deal with global climate change? It needs to, because as soon as we finish our warming trend and the Earth re-snaps itself back into shape, we'll end up having the opposite extreme for a while till it finds a happy medium. That opposite extreme will be an ice age. So as we conclude, I want to remind you that the Arctic regions are the most impacted, especially Greenland. I'm going to have you watch another video now. This one's only 5 or 6 minutes long, but it'll be the most important video you watch all semester. And this will be part of our discussion this week. So you have to watch this in order to do your discussion, and should have actually watched it by now. And it's part of Chasing Ice. If I could advise you to watch one documentary this semester, it would be this one, Chasing Ice. It was done by a geologist who got into photography and wanted to test a hypothesis about glaciers that were retreating, but he wanted to have documented proof in order to do it. His crew captured the largest glacier calving event in the history of mankind. And it's scary. This is just a snip from that to show you that they put a reference to the part of Manhattan to show you how big this section of this iceberg actually calved off, meaning it broke off of the main section of the glacier. That's a direct consequence of climate change. We're not talking about little bitty climate change here. We're talking substantial. This needs to be on your radar screen long term. Anyhow, climate change, it's going to happen whether we want it to or not, but we can do our fair share. So you need to consider what you can do to improve your carbon footprint, to improve the way that you deal with your recyclables, because whether you've realized it or not before today, all these things fit together. In order to get metals and things out of the ground, we use a considerable amount of heat to smelt those out. Well, those produce carbon, they produce methane, they produce NOx gases. These are all the things we're worried about with climate change. So recycle anything and everything you can, because it actually takes less energy to recycle in the manufacturing process than it did to make the raw material itself. I surely hope you've enjoyed this semester, and it's been a privilege to have served you. Thanks. Bye.